Hello everyone. We are going to start with the third module of our artificial intelligence course. This is the artificial intelligence fundamentals. The first topic in this module is knowledge representation, processing, and rationing. The agenda of this topic includes what is knowledge representation, different types of knowledge, what is the relation between knowledge and intelligence, techniques of knowledge representation, and representation requirements. The very important question is what is a knowledge representation? Humans are best at understanding, reasoning, and interpreting knowledge, but how machines do all these things comes under knowledge representation and reasoning. We can describe knowledge representation as following. Knowledge representation and reasoning is the part of artificial intelligence which concern with artificial intelligence system thinking and how thinking contributes to intelligent behavior of system. It is responsible for representing information about the real world so that the computer can understand and can utilize this knowledge to solve the complex real world problems such as a diagnosis, a medical condition, or communicating with humans in natural language. It is also a way which describes how we can represent knowledge in artificial intelligence. Knowledge representation is not just storing data into some database, but it also enables an intelligent machine to learn from that knowledge and experiences so that it can behave intelligently like a human. There are several types of knowledge. Declarative knowledge, it includes concepts, facts, and objects and expressed in a declarative sentence. Structural knowledge, it is basic problem-solving knowledge that describes the relationship between concepts and objects. Procedural knowledge, this is responsible for knowing how to do something and includes rules, strategies, procedures, etc. Meta-knowledge defines knowledge about other types of knowledge. And heuristic knowledge, this represents some expert knowledge in the field of or subject. What is the relation between knowledge and intelligence? In the real world, knowledge plays a main role in intelligence as well as creating artificial intelligence. It demonstrates the intelligent behavior in artificial intelligence agents or systems. It is possible for agent or system to act accurately on some input only when it has the knowledge about this. In this example, there is one decision maker whose actions are justified by sensing the environment and using knowledge. But if we remove the knowledge part here, it will not be able to display any intelligent behavior. Presentation, we are going to present 5 techniques of knowledge representation in artificial intelligence. Logical representation, semantic networks representation, frame representation, production rules representation, and ontology representation. Let's start with the logical representation. Logical representation is in a specific language with some concrete rules. Logical representation means drawing a conclusion based on various conditions. This representation lays down some important communication rules. It consists of correct defined syntax and semantics. Each sentence can be translated into logics using syntax and semantics. Logical representation can be categorized into mainly two logics, propositional logics and predicate logics. And the example about the propositional logic is the sentence, every car has 4 wheels, and in the simplest representation form, no details about the cars, the wheels, the number 4, and their interrelationship. So we can consider the following inference rule. Every car has 4 wheels. Some Fords are cars, therefore some Fords have 4 wheels. technique about the knowledge representation is semantic network. Semantic networks work as an alternative of predicate logic for knowledge representation. In semantic network, you can represent your knowledge in the form of graphical networks. This network consists of nodes representing objects and arcs which describe the relationship between those objects. Also, it categorizes the object in different forms and links those objects. This representation consists of two types of relations: is-are relation, that is known as an inheritance, and kind of a relation. The example about the semantic network is represented on this slide. So we have to follow the statements to represent them in the form of nodes and arcs. The statements are: Share is a dog, Share is a mammal, Share is owned by Mary, Share is white colored, all mammals are animal. So you can see the network, semantic network here. We have a node, dog, mammal, animal, Share, Mary, and white. And we have arcs between these nodes. We have three arcs that is a type is a relation, and this is an inheritance. The mammal is an animal, the dog is a mammal, Share is a dog, and we have two kind of relations. The first is about the color. Share is a colored white, and Share is owned by Mary. So this is the example about the semantic network. The next technique for data representation in artificial intelligence is frame. A frame is a record-like structure that consists of a collection of attributes and values to describe an entity in the world. These are the artificial intelligence data structure that divides knowledge into substructures by representing stereotype situations. Basically, it consists of a collection of slots and slot values of any type and size. Slots have names and values which are called facets. On this slide, you can see a simple example about the frame representation. The example is about the frame for a book entity. We have a slot, title, author, edition, publishing year, and pages. And we have a values about these slots: software engineering, Roger Pressman 9th edition, 2020, and 704. The next technique about the knowledge representation in artificial intelligence is production rules. In production rules, artificial intelligence systems checks for the condition, and if the condition exists, then production rule fires and corresponding action is carried out. The condition part of the rule determines which rule may be applied to a problem. This complete process is called recognized arc cycle. The production rule system consists of three main parts: the set of production rules, working memory, and the recognized arc cycle. You can see a production rules simple example. If at bus stop and bus arrives, then action get into the bus. If on the bus and paid and empty seat, then action sit down. If on bus and unpaid, then action pay charges. If bus arrived at destination, then action get down from the bus. Knowledge representation in our presentation is ontology representation. Ontology is a formal explicit description of concepts in a domain of discourse. Classes, sometimes called concepts, properties of each concept describing various features and attributes of the concept, slots, sometimes called roles or properties, and restrictions on slots, facets, sometimes called role or restrictions. An ontology, together with a set of individual instances of classes, constitutes a knowledge base. Ontologies are built to share common understanding of the structure of information among people or software agents to enable a reuse of domain knowledge, to separate domain knowledge from the operational knowledge, and to analyze domain knowledge. Ontologies are similar to semantic networks but have major differences. The create ontology, the specific language how web ontology language is used. It gives possibility to specify property characteristics, which provides a powerful mechanism for reasoning about the property. The how can also provide Boolean combinations, union, intersection, complement of classes, and the means to specify a class via direct enumeration of its members. On this slide, you can see a simple example about ontology representation. The example is about the domain ontology of shapes. You can see we have three concepts: shape, cycle, and square. There are two subclasses of relationships that represents inheritance in the ontology language, and the cycle concept has one property, radius. The radius property is functional, that is mean that each cycle has one radius. In the end of this presentation, I will present the representation requirements. A good knowledge representation system must have properties such as representation accuracy, inferential adequacy, inferential efficiency, and acquisitional efficiency. So these properties are very important to a good representation of knowledge. Thank you for your attention.
And the next topic of the Module 3 is Logic Programming and Introduction to Prolog. And what is Prolog? Prolog is programming in logic. It is invented in 1971 by Alan Cormier while visiting at the University of Montreal for the purpose of natural language processing. This language mainly developed and promoted in Europe, and you will use the programming environments with Prolog. It is the web-based programming environment. Prolog is a radically different concept of programming from more conventional computer languages such as C++, Java, Python, etc. Now, this language widely is used for different artificial intelligence applications. Prolog programs are simply knowledge bases consisting of atomic and conditional sentences. And now we can see the example for family as a program in Prolog. For example, John is child of Sue. John is child of Sam. Jane is child of Sue. Jane is child of Sam, and so on. This is the atomic sentences. And we can see what is the parent. Y is parent of X when X is child of y, or father. Father y is father of x when x is child of y and y is male, and so on and so on. Let's now we'll look at the pieces in details. Constants and variables in Prolog. A Prolog constants must start with a lowercase letter and can then be followed by any number of letters or digits. A constant may also be a quoted string. This is any string of characters enclosed with single quotes. So, let's see the next legal constants. Su with a lowercase, op, sex, member number 5, and this is the quoted string. Who are you? A Prolog variable must start with an uppercase letter and can then be followed by any number of letters, underscores, or digits. So, the legal variables are x with uppercase, p1, my dog, the biggest number, variable 27b. And what is the atoms or atomic sentences? These sentences of Prolog have the following form: predicate, left parenthesis, term 1, comma, term 2, comma, and so on, term k, and after that the right parenthesis. Some notes: immediately after the predicate, there must be a left parenthesis. Between each terms, there must be a comma, and immediately after the last term, there must be a right parenthesis. The conditional sentences of Prolog have the following form: had, colon, then hyphen, body 1, comma, body 2, comma, and body n, where the head and each element of the body is an atom. Some notes: immediately after the head there must be a colon, then hyphen. Between each element of the body there must be a comma. If n is 0, then this symbol should be omitted. In other words, an atomic sentence is just a conditional sentence where the body is empty. A Prolog program is a sequence of clauses, whereas clause is an atomic or conditional sentence determined by a period. A comment may appear at the end of the program or just before a constant or variable and starts with a %sign. The rest of the line is ignored. Here is a very short but legal program in Prolog, ZZZ dot. Here is a somewhat longer one, mortal X when X is man. All men are mortal. Socrates is a man. Socrates is a man. This is the sign. And a longer one still is the family example from before. Typically, a program is stored in a file with a name like family.pl or some other name with .pl. And how we use the Prolog programs? Prolog programs only do something in response to some question, to some queries. Here is the normal way of running a Prolog program. At first, we begin by preparing a file containing the Prolog program. The next step, we run the Prolog system and ask it to load the Prolog program. When we repeatedly do the following, we pose a question to the system and we wait for Prolog to return an answer. Often, we save these queries and answers in the separate file. And finally, we exit the Prolog system. This is the program environment SwiProlog. We can download SwiProlog and use it on our computer, and we try SwiProlog online. And when we download the SwiProlog in Windows, we will see this screen. At first, we load the file family.pl, for example, and we can see this information: family complied 0 seconds AFs. After that, we can pose some questions or make the query to Prolog. For example, father, Sam, Jane. This is the question: Sam is father of Jane? Yes. Prolog's answer is yes. This is success. And when we want to exit from Prolog, we type halt. Prolog under Linux or Mac operation system is similar. Let's see the simple queries. This is queries without variables. Posing a question or query is asking Prolog to establish the atom using backchaining, just as we did by hand before. If the query has no variables, there are three possible outcomes. The first, Prolog answers yes or true. The atom can be established. This is the situation in the form. We can see that the Sam is father of Jane. Sam is father of Jane. Yes, this is the true. The second outcome is Prolog answers no or false, when the atom cannot be established and Prolog runs out of alternatives to try. And the third outcome is when Prolog does not answer. The atom cannot be established and Prolog continues to try alternatives. And when we use queries or questions with variables, we have three possible outcomes. The first, Prolog answers no. The atom cannot be established for any value of the variables, and Prolog runs out of alternatives to try. The second outcome is that Prolog doesn't answer. The atom cannot be established for any value of the variables, and Prolog continues to try alternatives. And the third outcome is then Prolog displays value for the variables for which it can establish the query. At the point of the user has some choices: type a space or type return, in which case Prolog answers yes and the query is done, and type a semicolon, in which case Prolog tries to find new values for the variables with the same three possible outcomes. And let's see the example with the family. Our question is who is Sam the father? And this is father, Sam, comma, x. X is variable. We want to see only the first answer, and the prolog return x is John because Sam is father of John, and after that, yes, this is the trio. If we want to see who is the father of whom, the query is father YV, and this is two variables, and prolog return the answer Sam and John because Sam is father of John. If we want to see any more, we tap enter and prolog return Sam and Jane because Sam is father of Jane. And if we want to see any more, we tap enter and prolog return George and Sue because George is father of Sue. If we tap enter anymore, prolog answers no. And what is the terms? The term is a constant, variable, or number. What is the constant? This is one of the following: a string of characters enclosed with single quotes, a lowercase letter optionally followed by letters, digits, and underscores. A variable is an uppercase letter optionally followed by letters, digits, and underscores. A number is a sequence of one or more digits optionally with minus sign and optionally containing with a decimal point. In summary, a predicate is written like a constant. An atom is a predicate optionally followed by terms enclosed with parentheses and separated by commas. A literal is one of the following, optionally preceded by this symbol, an atom, two terms separated by this symbol. A query is a sequence of one or more literals separated by commas and terminated by a period. A clause is one of the following, an atom terminated with a period or an atom followed by this symbol followed by a query. A program is a sequence of one or more clauses. And programming in Prolog consists in writing clauses that fully characterize the predicates you are interested in. The easier part is writing the true, the whole true. The harder part is writing it in a way suitable for backchaining. A common concern is knowing when a variable gets instantiated, when using this symbol and arithmetic operations, or when generating a value to be tested. In some cases, predicates can be defined in a way that allow queries with variables to generate values. Let's program in Prolog the next simple example for Greek goods. We see Kronos and Rhea and their child Demetra, Zeus, Poseidon, Hades, Hestia. And daughter of Zeus, Aphrodite, and the daughter Athena, and Zeus' sons Apollon, Artemis, Hermes, Dionysus, also Ares, and so on and so on. We start the knowledge base. At first, the predicate man. Man is Kronos. Man is Zeus. Man is Poseidon. Hades is man. And Ares is man. After that, the woman. Woman is predicate with atom Rhea. Rhea is woman. Demeter is woman. Hera is woman. Persephone is woman. After that, we use the parent. Parent is predicate with two atoms. And we see that Kronos is parent of Demeter. Rhea is parent of Demeter. Kronos is parent of Zeus. Rhea is parent of Zeus. Zeus is parent of Persephone. Demeter is parent of Persephone. Zeus is parent of Ares. Hera is parent of Ares. After that, we can see the some conditional predicates. Father, X, Y, is that parent X, Y, and man X. It means that X is father of Y when X is parent of Y and X is man. The mother, X is mother of Y when X is parent of Y and X is woman. Daughter, X, Y. X is daughter of Y when Y is parent of X and X is woman. Son, XY, when Y is parent of X and X is man. After programming, we can ask Prolog for some facts. For example, we can ask Prolog father XY, that means who is father of whom, and Prolog answers that Kronos is father of Demeter, Zeus is father of Persephone, and Zeus is father of Ares. If we ask Prolog father Zeus Y, or Zeus is father of whom, the Prolog answers that Persephone and Ares are the values of the Y, because Zeus is father of Persephone and Zeus is father of Ares. Also, if we ask Prolog daughter X Zeus, that means who is daughter of Zeus? Prolog answers that Persephone is daughter of Zeus. And in the question son X, Y, Prolog answers that Zeus is son of Kronos, Zeus is son of Rhea, Ares is son of Zeus, and Ares is son of Hera. So we can expand the knowledge base and make some queries to Prolog and get answers of our questions. At final, we can see that in this way Prolog helps us make decisions and draw conclusions in system using artificial intelligence. The next topic in the module 3, artificial intelligence fundamentals, are searching, planning, and decision making. We can see what is uninformed depth search, and word-first search strategies, also informed heuristic search and A-star algorithm, and some applications. At first, let's see the problem-solving agents or PSA. We know that agents must find a sequence of actions to achieve their goals. Agents with goals have in mind future actions and how satisfactory the results are. A problem-solving agent is a variant of an agent with goals. They use atomic representations. For example, the states of the world are seen as a whole. Unlike them, planning agents are agents with goals that use extended, factorized, or structured state representations. And what is the goal and problem formulation? The first step to problem solving is goal formulation. A problem solving agent must understand how to act to achieve a target state. In order to do this, it has to decide which actions and states it will take into account when trying to reach the goal. Problem formulation is the process of determining the actions and states that must be considered to achieve a given goal. A problem solving agent doesn't know which the possible actions in the base because it doesn't know enough about the states that result from the execution of the individual actions. If it hasn't additional information, for example, if the environment is unknown, the problem solving agent hasn't choice but to randomly try an action. If it has the necessary funds, the problem solving agents can first explore the possible options before processing with the actual implementation of the actions. And assumptions about the environment. The environment has to be observable because the agent always knows the current state. Discrete. At any given state, there are only finitely many actions to choose from. Known. The agent knows which states are reached by each action. And deterministic. Each action has exactly one outcome. Under these assumptions, the solution to any problem is a fixed sequence of actions. And what is the search? The search is the process of looking for a sequence of actions that reach the goal. Search algorithm takes a problem as input and returns a solution in the form of an action sequence. An execution phase, once a solution is found, the actions it recommends can be carried out. Let's describe what is the formal definition of a problem. A problem can be defined formally by 5 different components. The first is initial state. This state that the agent starts in. For example, the initial state for an agent in Plovdiv can be described as in Plovdiv. The second, description of the possible actions available to the agent, presented as a function actions S. Given a particular state S, Action S returns the set of actions that can be executed in this state S. We say that each of these actions is applicable in S. For example, actions in Sofia is equal to go Athens and go Nicosia. The third is a transition model, a description of what each action does, specified by a function results as A that returns the state that results from doing action A in states. We also use the term successor to refer to any state reachable from a given state by a single action. Goal test is the four components. Goal test determines whether a given state is a goal state, and at final, path cost. This is the function that assigns a numeric cost to each path. State space is the set of all states reachable from the initial state by any sequence of actions. Together, the initial state actions and transition model implicitly define the state space of the problem. The state space forms a graph in which the nodes are states and the link between them are actions. A path in the state space is a sequence of states connected by a sequence of actions. An example for state space is a road map. If we assume that the states are not in this graph, this is the city C1, C2, C3, and the road between them from C1 to C5. For example, this is the actions, and all this road map can be present as state space. A solution to a problem is an action sequence that leads from the initial state to a goal state. Solution quality is measured by the path cost function. An optimal solution has the lowest path cost among all solutions. What is the search tree? Having formulated some problems, we now need to solve them. A solution is an action sequence to search algorithms work by considering various possible action sequences. The possible action sequences starting at the initial state from a search tree with the initial state at the root, and the branches are actions and the nodes correspond to states in the state space of the problem. The general search approach is connected with the next step. A search starts at the initial state. We know that the root node of the tree corresponds to this initial state. The first step is to test whether this is a goal state. Then we need to consider taking various actions. We do this by expanding the current state. That is, applying each legal actions to the current state, we generate a new set of states. We add new branches from the parent node leading to the new child nodes. A leaf node is a node with no children in the tree. The set of all leaf nodes available for expansion at any given point is called the frontier or open list. The process of expanding nodes at the frontier continues until either a solution is found or there aren't more states to expand. Search algorithms all share this basic structure. They are different according to the how they choose which state to expand next. This is called search strategy. Loopy paths or cyclic paths make the full search tree infinite even though the search space consists of only a few states because there isn't a limit to how often one can traverse a loop. Loops can cause certain algorithms to fail, making solvable problems unsolvable. Fortunately, there isn't need to consider loopy paths. Loopy paths are a special case of a more general concept of redundant paths which exist whenever there is more than one way to get from one state to another. For example, in the roadmap with the nodes of Plovdiv, Stara Zagora, Asenovgrad, Smolen, Karlovo, Kazanluk, and so on. Since there is a road from Plovdiv to Stara Zagora, obviously the road Plovdiv to Karlovo to Kazanluk to Stara Zagora is redundant. As the saying goes, algorithms that forget their history are doomed to repeat it. The way to avoid exploring redundant paths is to remember where one has been. To do this, we use the tree search algorithm with a data structure called the explored set, also known as a closed list, which remembers every expanded node. Newly generated nodes that match previously generated nodes, one in the explored set or the frontier, can be discarded instead of being added to the frontier. The frontier is a separator. The algorithm has another nice property. The frontier separates the state space graph into the explored region and the unexplored region, so that every path from the initial state to an unexplored state has to pass through the state in the frontier. As every step moves a state from the frontier into the explored region, while moving some states from the unexplored region into the frontier, we see that the algorithm is systematically examining the states in the state space one by one until it finds a solution. For example, let's see a rectangular grid problem. The frontier white nodes always separates the explored region of the state space red nodes from the unexplored region gray nodes. We can see that in the situation 2, just the root has been expanded. In the situation 3, one leaf node has been expanded. In the situation 4, the remaining successors of the root have been expanded in the clockwise order. The term uninformed search or blind search means that the search strategies haven't additional information about states beyond that provided in the problem definition. All they can do is generate successors and recognizes a goal state from a no goal state. Also, strategies are different by the order in which nodes are expanded. At first, let's see the breadth first search strategy. This simple strategy in which the root node is expanded first, then all the successors of the root node are expanded next, then their successors, and so on. In general, all the nodes are expanded at a given depth in the search tree before any nodes at the next level are expanded. This strategy is an instance of the general graph search algorithm in which the shortest expanded node is chosen for expansion. This is achieved very simply by using FIFOQ for the frontier. Thus, new nodes, which are always deeper than their parents, go to the back of the queue, and old nodes, which are shallower than the new nodes, get expanded first. And let's see some application of the breadth first search algorithm. This algorithm may be used to discover the location nearest to the specific origin point. This algorithm is used in peer-to-peer networks as a search technique to discover all neighboring nodes. This algorithm is used also in web crawlers to build web page indexes. It starts at the source page and works its way through all the next links connected with it. Every web page is treated as a node in the network search. The next search strategy is depth first search. It always expands the deepest node in the current frontier of the search tree. The search process immediately to the deepest level of the search tree where the nodes have no successors. As those nodes are expanded, they are dropped from the frontier, so then the search back up to the next deepest node that still has unexplored successors. This algorithm is an instance of the graph search based graph search algorithm where the board first search uses first input first output queue, and depth first search uses last input first output queue. That means that the most recently generated node is chosen for expansion. This must be the deepest unexpanded node because it is one deeper than its parent. As an alternative to the graph search style implementation, it is common to implement depth first search with a recursive function that calls itself on each to its children in turn. Depth first search algorithm is exploited in all of these situations. In scheduling problems, in cycle detection in graphs, in topological sorting, for finding solutions for puzzles that have only one solution, for example, Sudoku. This algorithm and this method is used in network analysis. The algorithm is frequently employed as a subroutine in more complicated algorithms. This algorithm is used in scheduling and finding spanning trees and also in mapping routes. breadth search strategy and depth-first search strategies. They are uninformed search strategies. An informed search strategy using problem-specific knowledge beyond the definition of the problem itself can find solution more efficiently than can an uninformed strategies. The general approach we consider is called base-first search. Base-first search is an instance of the general tree search or graph search algorithms in which a node is selected for expansion based on the evaluation function fn. The evaluation function is constructed as a cost estimate, so the node with the lowest evaluation is expanded first. Informed search is heuristic search, and the choice of heuristic function fn determines the search strategy. Most best-first algorithms includes as a component of this function a heuristic function denoted hn. Hn is equal of estimated cost of the cheapest path from the state at node n to a goal state. Heuristic functions are the most common form in which additional knowledge of the problem is imparted to the search algorithm. We consider heuristic function Hn to be arbitrary, non-negative, positive, problem-specific functions with one constraint. If n is a goal node, then heuristic function is equal to 0. The most widely known form of best-first search algorithm is called A-star search. It evaluates nodes by combining Gn, and this is the cost to reach the node, and Hn, the cost to get from the node to the goal. Fn is equal to Gn plus Hn. Since Gn gives the path cost from the start node to node n, and Hn is the estimated cost of the cheapest path from n to the goal state, we have Fn, it is equal estimated cost of the cheapest solution through n. The A-star algorithm has many applications. It is commonly used in web-based maps and games to find the shortest path at the highest possible efficiency. A-star is used in mainly artificial intelligence applications such as search engines. This algorithm is used in network routing protocols to calculate the best route between two nodes. Hello! Let's see what is Python programming and how this language can help us for programming realizing of artificial intelligence algorithms. The first question is why Python? Because Python is less code. Python has pre-built libraries. It is easy to learning. It is platform independent, and Python has the massive community that support. Stack overview calls Python as the fastest growing programming language, and we see that Python is the fourth language in these statistics. Python is an open source, object-oriented programming language mainly used for data science. Python has many artificial intelligence packages and libraries. At first, we can see the TensorFlow that has some features as a responsive construct. It is flexible, easy, trainable in parallel neural network trainings. This is the link of this library. It is developed by Google in collaboration with Brian team. It is used in writing machine learning algorithms. NumPy is a library with open source, and it is mainly used for computer science, scientific or math data. The features of the NumPy supports multidimensional areas. It is intuitive. It can be used for numerical analysis, and this is the link of this library, this artificial intelligence package. Theano is an open source library that allows us to define, optimize, and evaluate math expressions involving multidimensional areas efficiently. The features of Theano are integration with NumPy, transparent use of graphical GPU, and extensive unit testing and self-verification. The link to Theano is here. The other Python artificial intelligence package is scikit-learn. This PyLibrary is associated with NumPy and CPy. It is considered as one of the best for working with complex data. Some features of this library is cross-validation in supervised learning algorithms and feature extractions. Also, Keros simplified the process of implementation of neural nets. It is also provides some of the best utilities for computing models, processing dataset, visualization of graphs, and so on. Some features of Keros are runs smoothly on both CPU and GPU, supports all types of neural nets and completely Python based. NLTK is also the Python artificial intelligence package. The link is here, and it is open source library for natural language processing text analysis. The main features of the natural language toolkit or NLTK are studying natural languages, text analysis, and sentimental analysis too. And something for programming in Python. Let's we create our own code, and we have um, to describe the Python data types and some syntax. At first, numerical data types, integer, floating point, numbers, and boolean. We know that characters are strings with the length 1. We can converting from one type to another by using of um, this function int, float, double, boolean, string, and so on. Also, we can check type of variables with the function type. For programming in Python, we must say that white space matters. All lines with the same indentation are part of the same block. Mathematical and logical operators are minus, plus, divide, multiply, uh, percent, and logical operators and or not equal, different, less, great, and so on. Control structures are if else statement, while statement, for statement, break and continue statement. We see some example. We can create a list, iterate over lists with for loops, and also list can group many different data types. We can append the element of the list, the pop, insert, reverse, sort, and print the elements of list. For strings, a string is similar to a list but also from characters. To create a string, we can use different manners. With Python, we have to solve any problems, and here we can see some solving throughout Python. The solving hill climbing algorithm in artificial intelligence, for example. Some algorithms with informed search also. For uninformed search algorithms also we have some tutorials to use the Python for describe these algorithms and solve the problems. Best first search algorithm also, and heuristic search and minimax algorithms. We believe that with the accumulated knowledge of Python programming, we will be able in 7th, 8th to 12th grade in the school to use this language to solve some artificial intelligence tasks and problems.